Hello. Welcome to the session on resume-based WSGI Load Balancer by Jim Fulton. Jim Fulton is the ex-Pope. Well.
Hi. Thank you. I hope we can all stay awake in this last session of the day. I apologize for the title. I guess a lot of people think I'm going to talk about the resume-based WSGI Load Balancer, but I'm going to be talking about a resume-based WSGI Load Balancer. I guess I should have put content aware in the title. That would have been better. Anyway, I work for Zope Corporation, and we host several hundred newspaper sites. And a problem that we have is that our working set, how many people here are familiar with the term working set? Okay, well, so the idea of a working set is you've got some, maybe large set of data like a database, and you're going to be operating on it, and you're not going to usually need to, operate on all the data, but there's going to be some subset of the data that you're going to work on a lot. That's often referred to as a working set. And if the working set fits in memory or in your cache, then you don't have to go back to the database a lot, only when, maybe something changes in the working set. So, if you can, sort of a sweet spot is to have all of your working set, reside in your caches, ideally in the application's RAM. Unfortunately, with the applications we're doing, that's not really feasible. It's not even going to be feasible after we have the improvement of the resume-based load balancer, but it's going to help. So we have several hundred newspaper sites, a lot of data, more data than we can really fit in a single application. We have multiple layers of caching. We have, we'll look at that in a minute. And anyway, so the working set is too big to fit in memory. We have lots of workers on the order of 40 or 50. That's partly because of the GIL, because we can only use one CPU per worker. And also because the working set doesn't really fit in memory, we do lots of database access. Database accesses are slow. And there's actually sort of a secondary effect where if you're doing a lot of database accesses, not only are the database accesses slow, but if you have enough clients accessing the database, you actually make the database go slower because you're loading it so heavily, and then of course that makes all the database accesses go even slower. So our cache architecture is probably pretty familiar. We happen to be using ZODB, and I'm going to be talking about our use of ZODB primarily just so you understand the particular situation we're dealing with, but it really doesn't matter what sort of database you're using. You have this issue of needing to have access to the data and wanting to avoid trips to the database. But I'm going to be talking about ZODB. So we have our application, which is a web application. In front of the application, there's a HTTP cache, in our case, Squid. It has its own in-memory cache as well as a disk cache. We actually have two layers of Squid. And then they're talking to the application. The application has its in-memory objects as well as a local database cache. And then, of course, we talk to the database. So ZODB has this notion of an object cache. It's basically just a tree of objects in memory. The database, the ZODB database itself is very simple. It's basically, you can think of it as a mapping from object IDs to database records, where the database records are pickles. The object graph is simply a tree of the objects that you happen to be using at any point in time. And then ZODB provides facilities for moving things out of memory, either to free memory for other objects or because they've been invalidated by somebody changing them. And the object cache is per application thread. So if you have a multi-threaded, if you have multiple application threads, you'll have multiple copies of the object cache. There's also a client cache, which is a disk-based cache of database records. We have this because database records are smaller than the objects in memory, and plus we compress them, which makes them even smaller. And also potentially the database cache can be, larger than the, the RAM that you allocate to the application. I say it that the disk cache, that the local disk cache can be larger than what you can fit in RAM, but in practice, because disks are so slow, you actually want the disk cache to fit in memory as well, and you want the local database cache to fit in the local machine's disk cache so that you're not going to disk to get its data. So loads from the Zio client cache on the machines that I use take about 20 microseconds if the record is in the system's disk cache, and about 100 microseconds to process, to decompress and deserialize the data. If I have to go to actual disk, or if I have to go to the database server, then we're talking milliseconds, which by today's standards is a really long time. On the machines that we buy, it's uneconomical to have more than 4 gigs per core. So we typically have 4 gigs per core, and we use that both for the objects, the application's own memory, and to try to make sure that the database cache fits in the machine's disk cache. Because Python processes can't use more than one processor for the most part, then we only have one application thread per process. And in an ideal world, for the kinds of applications we write, we want to be CPU bound because we don't really want to be slowed down talking to the database. So anyway, this leads us to having a process per core and about 4 gigs per process. We've got our eye on EC2, and sort of one of the standard sizes, well actually most of the sizes on EC2 give you about 2 gigs per core, some a little bit more, some quite a bit less. So it'd be better if we could fit in 2 gigs. In fact, it'd be ideal if we didn't need the Zio disk cache at all. One common solution to this sort of problem is memcached, where you have a cache that's shared among multiple applications, and so you can have that cache be a lot larger than the memory that you allocate to the individual application, and that's particularly valuable for something like an expensive SQL query, but it's not a super good fit for ZioDB, because ZioDB you're doing lots of really small queries that aren't really queries at all. They're fairly fast object accesses, but if you have to go to the storage server, you're still talking milliseconds. In my measurements of using memcached and other IPC techniques, I generally, round trips were on the order of 100 microseconds, which again is kind of long. It's more attractive than, say, doing a millisecond access to disk or a couple of milliseconds hitting a database server, but it's not very attractive compared to hitting a local Zio cache, and of course it'd be better if we didn't have to go to it at all. In addition, we've got these squid caches, and a problem that we've had with them is the same problem we have with our application caches, which is that each squid cache ends up having to cache the entire corpus for several hundred papers, and we end up having our caches not really being big enough to be as effective as we'd like. They're fairly effective, but not as effective as I think they could be. So the approach that we decided to pursue was to try to spread the corpus across workers. So try to find some way that the working set could be split up so that different workers worked on different parts of it, ideally as independent as possible, and so that each worker had a much smaller working set, maybe as small as 1 over the number of workers. And so the way we do this is we classify requests using an application-provided request classification function, and then we send different classes of requests to different workers. And this is an alternative to sort of manually trying to split up the requests into pools, which we've done once on one level, which helped, but it's really not practical to sort of deal with 400 different sites on that level. So we really need something that's automated. So the resume-based load balancer, it's a specialized load balancer that routes requests based on what skills a worker has for a given request class, and also how busy that worker is. And some requirements we had is that the knowledge of what workers are good at needs to survive load balancer restarts. In fact, we really want to be able to have multiple load balancers for availability first, and second, these are written in Python, so they're often going to be fast enough, but it's nice to have the option of sort of spreading that load around among multiple load balancers, all going against the same set of workers. And of course, this really needs to be automatic. So basically, the first step is to classify requests. You supply, and actually often you'll just use one of the built-in ones, but there's a function that takes a WSGI environment and returns a string, which is the request class. There are a couple of built-in classifiers. One that's for host-based request classification that simply looks at the host header, strips off a leading www.prefix if there is one, and then uses the host name, which is actually pretty effective for our case, at least for the most part. Or at least should be. There's some idiosyncrasies in our stack of caches and things that the host header actually gets lost. So we end up doing something slightly different. And then there's another classifier factory that takes a regular expression and the name of a key from the WSGI environment, and it simply applies that regular expression to the key, and the regular expression has a named group that then, if the regular expression matches, then that group is extracted, then that's the request class. But you can supply whatever sort of function you might need. So, the load balancing algorithm is pretty simple. I've actually iterated on a number of different variations of this, but basically, for each request class, there's a list of skilled workers, and for most request classes, that list is of length 1. We basically pick the worker with the lowest weighted backlog, where the weights of the backlog are basically the worker's skill, which is essentially the number of requests per second that it's done in the past. And then if a worker's so a worker's backlog is basically the number of outstanding requests. And so if a worker's backlog is larger than the variance times the mean backlog of all workers, where the variance is a configuration parameter, then we give the work to some other worker. So basically, when the worker's backlog gets too high, we don't send work to it. We pick possibly an unskilled worker, and now that new worker becomes part of the pool for that particular request class. And so the request classes don't actually tend to be equal in terms of the amount of work that you need for them. And so the request classes that require more workers then sort of automatically get assigned extra workers as needed. So that's pretty simple. There's also a secondary benefit of this algorithm, which is that you can't have more than 1 over the variance workers assigned to a particular request class. It's just sort of an outgrowth of the algorithm. And this actually is pretty valuable. There's one of the first algorithms that was in this line was something called LARD that was developed in 1998. And one of the problems the author noted was that if the server that was suited to a request wasn't available, they would give it to another server, and under very high load, the whole sort of thing would break down because eventually you'd end up spreading the work to all your servers. And so with this algorithm, you can't use more than 1 over the variance servers for a request class. If a site is getting DDoSed, or in our CMS, we'll sometimes have operations that take a long time, and if the user gets impatient, they'll hit the reload a few times, and the users end up sort of DOSing the rest of the users of the CMS because all of the sort of application threads get tied up with that request, and this actually prevents that. So it was kind of a nice outcome of this. So the other part of this is the worker. So in this load balancer you have, well, let me back up. So in a traditional load balancer, you have a load balancer that's making HTTP requests to workers, and it really doesn't get any feedback from the workers other than how long they take to do a particular request. Whereas here, the workers periodically can send their resume back to the load balancer. In fact, the connection, as we'll see in a moment, between the load balancer and the worker is a custom protocol. And in fact, the workers are really part of the load balancer. We'll say more about that in a minute, but the worker's responsibility is to maintain their own resume. And periodically, well, when they're first connected to by the load balancer, and keep in mind they could be connected to multiple load balancers, they send their resume to the load balancer, and then periodically they update their resume, or, well, they're updating their resume all the time, but periodically then they'll send that resume to the load balancer to update it. And that resume is really just a mapping from the request class to the sort of the average request per second that worker takes to do that request class. Assuming that you're using some sort of database that keeps track of worker registrations, and I'll say a little bit later about how we're using Zookeeper for that, then the load balancer can notice when workers come and go. And so the way we run the load balancer is with Zookeeper, and so whenever a new worker appears, it registers itself with the Zookeeper, the load balancer notices that, and then automatically adds the worker to the pool. Similarly, when a worker goes away, the connections to the workers are long-lived. So when the TCP connection goes away, the load balancer notices it, and it removes the worker from the pool. If there are any in-flight get or head requests, and if they haven't generated any output to the browser yet, then they'll be retried with a different worker. And of course, any new work automatically shifts to other workers. So basically what we have is, the way we'll be deploying this is we'll have a traditional load balancer, probably HA proxy, that is set up with Heartbeat, and it'll talk to the Python load balancer, of which there'll probably be more than one, probably 3. And then that load balancer will talk to the pool of workers for any particular pool. The connection between the traditional load balancer, or if you didn't have a traditional load balancer in front, but from the browser, would be HTTP. So the resume-based load balancer is an HTTP server, and then it talks to the workers over a long-lived multiplex connection, sort of in the same spirit as something like FastCGI, except it's marshaled whiskey environments going over the wire and marshaled whiskey response coming back over the wire. And again, that's multiplexed, so there can be multiple requests in flight with a particular worker. This is implemented with gEvent. I actually looked at 0MQ, but I actually felt I actually like the fact that TCP takes care of letting me know about sessions, and so I ended up using gEvent. I'm quite happy with it. This was the first project I did with gEvent. It has this notion of greenlets, which are kind of like threads, except it's not what's the word? Not preemptive, huh? Well, cooperative multitasking. Thank you. And actually, in gEvent, you really don't need to even pay attention to greenlets unless you want to. Like, for example, if you wanted to integrate gEvent with some async API or some sort of API that it's not already integrated with, gEvent, especially for networking, sort of provides some high-level abstractions that are pretty nice. It has a whiskey server with HTTPS support. It supports thread pools, which if you're doing anything that blocks, as nice as async APIs can be, you really need a thread pool. And I found it easier than either threading or event-based programming. I'm still not totally satisfied with the way my tests work. They still feel kind of like the same sort of tests that I would write for a threaded program. I hope I'm doing it wrong, but I haven't had really taken the time yet to really think hard about how I can make that better. For the load balancer itself, the asynchronous I/O is, the load balancer is kind of the sweet spot for this kind of framework, where all you're doing is moving bits between sockets. It's really well suited for that. On the workers, you don't have to, but at least for an application like ours, like an application like Zope or Django or Bobo or whatever, Pyramid, you typically would use the thread pool. And in my test, which was sort of handing requests to the load balancer and as fast as I could and stacking them a few requests deep, the load balancer consumed about 4% of CPU, which isn't bad. It probably had a little bit easier job because the application I was hitting wasn't exactly fast, but anyway, it sort of didn't take an inordinate amount of resources. Now, lately or I especially, and I'm kind of dragging the rest of my company along, have gotten enamored with Zookeeper. A lot of times you have network services and they need to know about each other, and letting them know about each other manually through configuration files is just excruciatingly painful if you have any level of complexity or if you have workers that sort of come and go. So Zookeeper was designed to be sort of a coordination mechanism for applications, including being used for distributed locking and other sort of concurrency protocols. My use of it is fairly lightweight. I'm simply using it as a service registration and discovery mechanism. But basically, the workers register with Zookeeper, and then the load balancer discovers the workers by watching the Zookeeper nodes and is notified whenever a new, basically whenever a child node is added, which indicates the appearance of a worker, or removed. You can also store data on Zookeeper nodes. Basically, Zookeeper is a sort of a simple database of a tree structure, a tree of nodes. And being nodes, of course, they have potential children, and then they also can have data. And then I've written a package called zc.zk, which then provides high-level semantics on those nodes as far as data goes. So you can have properties and symbolic links and things like that fit well the sort of use cases that I've been using it for. And so we can also store configuration data on the nodes, and so you can easily tune the application at runtime if you need to by simply updating the nodes, and then both the workers and the load balancer can get their configuration from those nodes. And we've actually, as we've gotten into this, we've sort of gotten into sort of modeling our applications as trees. I think this is going to work really well for this. We're still sort of getting started, but here's sort of an example, a fairly simple example where I have a top-level node that's the load balancer. You can just kind of, you don't really need to understand this. You can just kind of squint and look at it and see if you can get a general idea what I'm talking about, and ask me more later. But the lines that begin with slashes are nodes, and so we have a resume-based load balancer pool. Well, actually, we have the resume, the EE resume LB, which is the load balancer. We have a variance. It has a variance property which controls this variance that showed up in the description of the algorithm. It has a provider subnode where it registers. So, for example, if we had multiple load balancers, you could have an upstream load balancer looking at that node and noticing where all the load balancers it's supposed to send requests to. It has a worker subnode, which has a provider subnode where all the workers register themselves. So that's how the discovery takes place. By sort of a systematic layout of this, we can do things like generate network maps with GraphViz that sort of show how a larger application fits together, which is kind of cool. But if you want to learn more about that, look at the ZCZK package in the G Shop. So to evaluate this, I actually spread the evaluation over a fairly long time, trying to be fairly careful. Thank you. Initially, I did simulations with simple Python WSGI apps that basically took integers representing objects that they might have in their cache, and then whenever they didn't have that integer in their little cache data structure, they would they would sleep for a period of time, and that sort of allowed me to validate the basic idea. I mean, I was pretty sure it would work, but it's nice to actually see it in some simulation. Then I moved on to a test where I got some access logs from our production servers and played them back against a load balancer configuration with the real applications and with production data. And in doing that, I found a number of issues and tweaked the algorithms a bit. And then finally, very recently, we started a production testing where we're actually using the load balancer in production alongside other nodes that are managed by the upstream load balancer. So basically, we have an IPVS pool. IPVS is a traditional, it's actually a layer 4 load balancer. And it has a pool of workers of about 31 workers, one of which is the load balancer, which then has 8 workers behind it. I'll say more about that a little bit later. So for the log playback test, I was fortunate enough that we got in a new app server, and I grabbed it before anybody else could have it. It had 8 cores and 32 gigs of RAM. I ended up putting 16 worker processes on it, and as I said, I played the access logs with production data. Also played back, did baseline tests. The baseline tests were important because the performance was going to be hindered by the fact that even though, by the fact that the 16 processors were really running on 8 cores, so they weren't going to run at the same performance levels, at least as far as CPU is concerned, as our production application instances. In this test, with 16 workers, we had about a 90% reduction in database loads, which is pretty good. We had about a 33% improvement in speed, which again is pretty good. I could wish for more, but it's not bad. I'll take 33%. Interestingly, I looked at the overlap between the databases. The ZODB has a cache, a disk-based cache, as I mentioned before, and I could find out what objects were actually used by those processes by introspecting the cache and seeing what objects were in the cache. I was really surprised to see that even for the baseline, where there's no request ordering, where all the workers are basically getting requests pretty much randomly for the whole corpus, that there was only about only about 33% of the objects were in all 16 of the caches, which I was really surprised. I think that's a result of the corpus just being so large that objects come in and out a lot. Unfortunately, these sites get a lot of bot traffic, which tends to hit a lot of long-tail content. So you get a lot of content moving through that, not to service humans, but to service bots. But with a resume-based load balancer, that cut down to about 7%, which is reasonable because there's certain objects that are in common. There are, these sites have ways of sharing content across sites, and there's certain centralized data. So 7% didn't really bother me too much. Again, I was kind of surprised at the 33, but you could see that in fact we were segregating the data quite a bit. So the production test was with the same machine, but this time I ran only 8 workers because I wanted to fully utilize the cores and compare to the actual production configurations of the applications. So with that, with only 8 workers, I got about an 80% reduction in database loads, which is pretty good. And this time, because I wasn't sharing a core with another worker, the CPU usage was a smaller amount of the actual time, which meant I could get a lot more benefit from the actual database savings. So this was about a 45% speed improvement. And I think in production we'll probably have about 20 workers. And so I have a feeling that we'll be able to do a fair bit better than that. There's still quite a bit of CPU going on in these requests, which now that we've really sort of kind of nailed the database access, I think we can start putting a little bit more focus on some of that optimization. Now, this is just a sample application. We use ZODB, but really the core idea of this doesn't depend on ZODB at all. I think the basic approach should be applicable to any application. Of course, your mileage will vary a lot, depending on your application, depending on the way your data is accessed, and depending on whether you can actually come up with a classification function that allows you to sort of divide up your working set across different workers. This is still kind of, well, no, this is still experimental. We are running it in production. And I think I think most of the testing for us from here on in will be in production. Some issues that we've identified is that I think there are sort of situations where if the load is light, you may have trouble with new workers actually getting work because the algorithm favors, skilled workers. So the algorithm may need some sort of tweak to allow workers that aren't getting enough work to be able to get more. We had a weird thing when in our initial production testing. We used the host-based classifier and then discovered that because of the way our stack was constructed, that the host headers were actually getting lost, and every request had the same host header. So basically, we thought we were running the resume-based load balancer, but we essentially weren't. And the performance reflected it. So then when we figured out our error, we fixed the request classifier, and yet it didn't recover. Maybe it would have if we'd given it more time, but PyCon was pretty close, so I didn't have a lot of time. So I ended up deleting the resumes and restarting, and then it behaved as expected. So we'll need to investigate that a little bit. So there's, other sorts of alternatives to this. First of all, sort of the classic load balancing approach is, well, there's some variations. One of the most solid sort of, default approaches is something called least connections or possibly weighted least connections. Lots of people mention round robin, but that hardly seems like a balancing algorithm to me. But anyway, so, sort of certainly the algorithm that we've used a lot has been least weighted connections, where basically you hand off to the worker that's the least busy. And in the resume-based load balancer, there's still sort of the same thing going on at a couple levels. First of all, if there are multiple workers for the same request class, then the algorithm within that class is essentially least weighted connections. And also, because of this notion that we're not going to get any backlog get unusually large, then you have this other sort of balancing. Again, I think we'll probably want another level that operates less frequently to maybe do a little bit more balancing of work across workers. Some other approaches are either IP or site affinity, where requests from a given IP always go back to the same worker, and that's useful if, for example, you have session data that you want to retain and only store on one worker. Or site affinity, similar sort of situation. Another approach, which is actually sort of the same thing, is some load balancers will set a cookie indicating which worker handled the request, and then keeping requests that have that cookie going to the same worker. Of course, the problem with those approaches is that if the worker dies, then you lose the affinity. And plus, for something like, say, IP affinity, if that IP actually happens to hit multiple request classes, then that doesn't really work too well. There were some other algorithms like LARD that I mentioned earlier, and there's another one called workload-aware request distribution that tries to analyze access logs and to try to figure out how much work different workers or different sorts of request classes are doing. I think those sorts of approaches are hampered by only having HTTP as a connection between the load balancers and the workers. By actually having a custom protocol where the workers can give feedback to the load balancer, in this case, in the form of the resume, gives you a lot more flexibility. And of course, having the workers be responsible for the resume, which avoids a lot of sort of coordination problems if you have multiple load balancers. I expect over the next few weeks to have this fully deployed for our applications in production. And then the next step that I'd like us to do is to move our HTTP caching down into the Whiskey stack so that it benefits from the load balancer. So as I mentioned before, our squids each cache the entire corpus, which is extremely inefficient. If we move response caching into the Whiskey stack, then the cache will only have to cache data for that particular request class. So the current status is it's in what I'll call testing production. So it's being used in production, but in sort of a slightly harebrained way where it's not sort of the same rigidity of our typical deployments, and in a way where we can sort of tweak it and where we can easily sort of back it out. It's released as a ZC resume-based resume LB package in PyPy, and it's in Subversion at those URLs. So, do you have any questions? And that, if you want, that you can get the URL from Questions?
Yes, I actually have one. Yeah, so my question is regarding the new workers that are still unskilled, and the problem where they might not get work.
Yep.
Have you considered the idea of forcing like a sample of the requests maybe being like duplicated to these just so they can like build their resume or something like that?
Right. I actually did that at one part in the process. One of the things that that makes that a little bit challenging is that you then have to also, which maybe is probably what we'll end up doing, but you then need to really sort of have some measure of the sort of impact of each request class so we know which work to move. But yeah, that might very well be something that we'll do. Now, that doesn't help. This might not just apply to new workers, but one thing that we ran into in testing was we had a worker that had plenty of things in its resume, but it wasn't the best thing at anything. And so again, it never got any work. If we sort of cranked down the variance measure so that work was spread more, then we could force it to get work, but then that would also cause work to go to other busy workers as well. So I think what I ended up doing was a slight tweak to the load balancing algorithm that took care of that case. But I think in order to address that, if I have to address it, I'll have to start actually keeping some sort of measure of the weight of each request class. Yeah, if you walk to the thing, you won't have to raise your hand. Save lots of energy that way.
First, thank you, great talk.
Thanks.
It wasn't clear, maybe I missed it at the beginning. Is this an algorithm you developed, or are you just implementing another published algorithm?
It's an algorithm that I developed.
Oh, cool. Is it documented somewhere, or is it just the code for now?
Yeah, it's right.
The code, okay.
That was in the slides, yeah. Yeah.
Okay.
And hopefully I didn't rediscover something that was published and just missed it, but.
Any chance of automating the resume? Any sort of tokenizing and using something like I'm sorry, not the resume, the classification? The creating of request classes? No?
I don't know. It's a Python function. I mean.
Right, so tokenize the request in some way and then do kind of like a Bayesian match on that. Could that be used? Or?
I don't know.
Possibly, okay.
I'm not entirely sure what you're talking about, but.
Well, maybe I'm, yeah.
No, I mean, this is, you know, I should point out that, you know, I think this is an interesting idea. So, you know, I'd be happy to see people take it and put it in other systems and run with it. There's certainly lots of opportunities to try different things. But it does provide a hook so that if you can think of some other better way of, you know, classifying requests sort of dynamically, then I'm not sure how that would work, but maybe if somebody explained it to me or if I thought about it harder, I would, yeah.
Cool.
So you said I guess the whole stack operates I guess 500 different newspaper sites, and so
right.
For every single, I guess, web worker, are they able to provide a response for every single site, or? Well,
So in our current configuration, any of the 50 or so workers could be called on to actually, we've actually divided our sites in badly, manually, so that there are actually two pools, and one pool has about 8 really big papers, and then another pool has all the other sites, plus some sites that are aliases for those 8 papers. But so there's a pool of 30 and a pool of like 20. And for each pool, it could handle requests for any of the sites that go to that pool.
Right,
With the load balancer, of course, then that gets divided up into much smaller sets.
So I would also assume that, I guess, there are certain, I guess, differences between each site, and so as the request comes in, you'd have to maybe load up settings, or maybe like this particular site has to,
well,
it's configured in a certain way.
So one of the things about using ZODB is it's all in one big pot. And
Okay.
so each site has a bunch of data that's specific to it, some of which is configuration sort of data, and some of which, most of which is content.
Okay. And so you just pull that out of ZODB?
Right.
When,
Well,
okay.
and of course, ideally, you don't want to pull it out of ZODB. You want it to just be in memory, which the way ZODB normally works, in the perfect case, is your working set is just in memory, and it's just a tree of Python objects. There are no
Yeah.
queries or anything.
Okay.
That's a sweet spot.
Okay. Hey, thank you.
Yep.
If you had to predict, how do you think this sort of load balancer would work in a more write-heavy environment?
Of course, if write is, if you're ultimately writing back to the same database, and that ends up being your bottleneck, it won't help at all. Write heavy, the application we have actually has both a CMS side and a delivery side. Our initial tests are with the delivery side, but I see a lot of benefits for the CMS side, which is write heavy, although this isn't a very write heavy app. But of course, those writes tend to be associated with a lot of reads. And so our slowest requests tend to be our CMS requests, where somebody does some operation that needs to search through a whole bunch of content or something like that. And so to the degree that the write operations tend to be associated with lots of reads, it would benefit. But of course, it doesn't apply to the database server itself. Okay, thank you very much.